So good afternoon, everyone. Everyone get seated. We'll be ready to start for this afternoon. So I'm Mike Schmidt. I'm Director of Software Engineering at AMD, working on computer vision. And I thought I'd just sort of start with sort of the history. If you've probably seen me here before, if you've been at these. For the last 4 years, we've been incrementally delivering software that we've talked about at these Khronos tutorials. We started with OpenVX release to open source in 2016. 2017, we put some layers on that help you do 360 video stitching. Last year, we showed our implementation of neural net extensions for OpenVX. And this year, we're going to show what we call the ROCm MIVisionX Toolkit. And there's some links here, and they'll be later in the slides as well, and during the tutorials. So what is MIVisionX? So essentially here, we're showing here what is in the package. So it's the OpenVX implementation, along with neural net extensions, along with a model compiler, model optimizer for running inference. There's a OpenCV interrupt. There's WinML that allows you to run this on Windows besides just on Linux. And there's a bunch of little utilities that come with it, including ADAT, which is a data set analysis tool, so helping you actually create and maintain and validate the data that you're using to train your neural nets on. There's a RunVX, which is a OpenVX command line tool that allows you to help you debug and run code. There's a tool called GDF, which is a graph description language, which is a scripting language. And I was really happy this morning to see the new graphical tool, which is even better than this, to actually allow you to visualize what your OpenVX graph looks like. GDF is basically a command line version of that, you might think. And Loom Shell, which is the 360 video stitching library. So MIVisionX is basically a tool that allows you to merge computer vision, classical computer vision kind of things, which are in OpenVX, with your neural net trained models. It's all open source, and we'll be showing you a tutorial. There'll be tutorials later on this afternoon that basically walk through several examples. I'm just going to sort of show you a high-level overview of what those things are, and I'll try to do it briefly because a lot of the slides that I have here are replicated later. So I'm going to give you the overview, and then you can actually see it in more detail later this afternoon. But here's sort of the big picture that you can think of. You start there on the left with your model that you've created, and you use a framework such as TensorFlow, Caffe2, PyTorch, any of those. You export that model that you've trained, and that's where we're not talking about the training today. We're talking about the inference. You export that model into an exchange format such as the Khronos NNEF, which we support, as well as the ONNX. And actually, I think someone's talking about a tool to convert back and forth between those. But essentially, you get that trained model as your input. And then you run our model compiler, model optimizer, and you generate a binary or a library. And we're showing 4 different options here of how you can actually do that. And that then becomes a component in your application that you actually deploy. So the concept is pretty simple, but the last 2 days at the conference, people down in our booth, they came up and they say, how do I go about creating an application? And this basically is the high-level overview of how you do that. You have to start with some data, right? And you have to train a model. So you have to sort of already know what your final application is going to look like in order to actually get started. And that's sort of similar to all neural net kind of things that have to do with vision, right? You're going to be doing image classification, you're going to be doing object detection, something like that. You sort of have to already know what your end app is going to look like, and then you can get started with this flow. So this is the way the whole stack looks like on an AMD device. You can see down at the bottom is the actual hardware, and up at the top is the application. In between is all the layers of stuff that you might have to go through, right? Of frameworks, exchange formats. All that orange part is the AMD middleware components, and the ROCm part, you can see all the compilers there. So ROCm stands for Radeon Open Compute Platform. I know the acronym doesn't exactly match the words, but it was a marketing decision to call it that. HIP is another one that's a little bit of a tongue twister, Heterogeneous Compute Interface for Portability. And what that is, that allows you, it's a source code translator that actually allows you to take CUDA code from an NVIDIA platform, translate it into a format which is now portable between AMD and NVIDIA hardware and compilers. And so it basically changes some of the source code and allows you to go back and forth. To actually implement everything we're doing in the tutorial, you don't actually need to do that, but if you did happen to have CUDA code, this is a tool that converts it. Okay, so these are the tutorials. We have 4 of them set up. Depending on how fast the guys from my team are in doing it and how fast everyone is to actually keep up with the tutorial on your machines, we may or may not get through all of them. But essentially, there's an image classification using ONNX. There's an object detection from Café. There's an image classification with NNEF, and then an object detection with multi-stream video decode. Now, those are not, like, we're not doing ONNX with image classification because that's the only way to do it. We're just trying to show an example of each one, right? And so we just picked a model that went with different examples. Again, you can see the links that are there. This is mainly for people that see the slides afterwards. You should be able to get this during the tutorial. Okay, so this is what the room setup is for the tutorial approximately, because I made this slide before we actually set up. So everyone should be able to be hooked up to Wi-Fi that has your laptops, right, in order to be able to run the tutorial. So the way we're going to try to run it is through the cloud. So we have this AMD servers that you'll be able to connect to. And where's Carrie? Yeah. So did you pass out the forms? Pardon? So everyone should get. Okay, yeah. So pass them out. So we're doing this now, but this is for the tutorial in an hour. So if you actually have issues getting connected, the guys from AMD will come. You know, you can raise your hand after you get the form, and they'll come around and make sure that you're actually pre-connected. So we can be doing that during the next hour, right? Well, you'll see when you get this form, there's instructions on how to connect your laptop, and then there's an actual, each person has a different port that they're going to connect into on the system so that everybody's set up. Now, we don't know if we're going to be able to run everybody in the room simultaneously, not because the server can't handle that many users, it's because we're not sure about the Wi-Fi speed. I did a speed test earlier. It was like 0.4 megabits, which is basically enough to do a 1980s teletype. So we'll see how well it works. Now, you won't actually be doing, for most of the tutorials, you won't be doing something that has a lot of bandwidth, except that 4th one that's doing video. We may have to voluntarily have people not run it while only one person runs it at a time to see if it works. I'm not sure how well the video is going to work. Okay, so you'll be getting those. So this is just a brief summary of what is in these tutorials. Essentially, the first one is doing image classification. So essentially there'll be some images like this golf ball, and when you run the application, it'll see the image and then tell you with whatever confidence number, is this a golf ball or is it something else? Right. The second one is object detection, and this one it's the same basic idea, except there'll be bounding boxes and labels inserted onto the image that you can see. By the way, if anyone has any questions about what this is, feel free to ask. Okay. The number 3 is image classification using NNAF. And then the last one is a multi-stream video decode using hardware decode and doing the object detection on top of it. Okay, and just this is just a quick more details on what's happening during the image classification demo, and this is the same thing that we're running in our booth downstairs the last 2 days, just so you understand the concept of how it might work and how we go about and how we constructed this demo. Essentially, there's a client and a server. They can be separate machines or the same machine, and the client basically does a setup to the server saying, this is the model I want to use, these are the parameters, and then the model on the server gets compiled and sends a status back to the client saying that it's ready to run. And then the client then sends images, and that's starting with the label A, sends images to the server. The server then does a decode of the image, and then it sends it into a GPU on the server. That's D and E on the list. It then does the image class, runs the network on the GPU, gets the result, sends it back to the client where it accumulates the results and keeps some statistics. This is basically an analysis of how we go about actually evaluating the performance of something like this. You can see all the steps A through G on there, and then what the step is, and then in the first row below that, I'm showing like what's the bandwidth or amount of bytes being processed. And then in the bottom row there, there's a list of example devices and how fast they can process that. So in other words, on the reading of the images, you could have different speeds of hard drive. So you might actually, when we run this on a big enough server, we actually exceed the throughput of a hard disk drive, right? So you have to go from a rotating drive to a SSD to actually be able to keep up, for example. For the purposes of today's tutorial, you're just going to get it to run. You're not going to actually do all this tuning that we're talking about here. So any questions on any of this? Oh, okay. So this is the tool that does data set analysis. So we don't really know of any other tool that's like this out there. And part of the way that we came about this was we needed to have a lot of test data to actually test and demonstrate some of these these samples and demos. Well, if you know anything about like the ImageNet database, it's meant for non-commercial use and for academics to do research on. And if you actually train on the images, that's okay, but if you actually take the images and you actually display them publicly, commercially, that's not actually covered because they basically collected all the data sort of without permission. And we've been using it for a decade, but technically a copyright holder of those images might not want you to be showing them. So we collected our own images, but then we had to say, well, are our own labeled images, how good are they? Are they, you know, when we run these, what percentage of time do we actually detect the things correctly and not correctly? And we had lots of images. So you can see in here we have 9,880 images, and some of them, 1,900, have no ground truth. 7,900 have the ground truth. The reason some of them have no ground truth is the ground truth was not something that matched into the ImageNet 1,000 classifications. So there, if you know the ImageNet database, there's things like elephants and you know, Indian elephant, African elephant, but dogs and lizards and other things, there might be things that are similar to things that are in the database, but they're actually something different. So we have some that are different, sort of as a negative test to see, are things that aren't in the database actually detected as things that should be. Anyway, so these are some statistics. The tool actually runs your image classification and then generates HTML, and then you can scroll through this HTML. I just have this one PowerPoint slide, but you actually might generate hundreds of pages of data. You can start with, and you can sort it by different object types and see how many of them were matched and not matched. You can sort it by confidence. You can look at it by drilling all the way down to individual images and view the image and try to figure out why the label was wrong, or how many things with the certain labels were not found because they may have been typos in the labeling or things like that. Okay. Oh, yes.
Quick question. Are your images copyright free? In
no.
your desk? No.
Our images are Mike Schmidt AMD images that we did not publish to the open source. So everything we're showing today is actually open source and everything except for these images. And we're just keeping these images within AMD because we don't want to actually go through the legal trouble of verifying that I actually took all the pictures. I took about 98% of them. But in order to try to get, so this database has about 800 out of the 1,000 classes in ImageNet. And so as I've been showing these, people around the world have sent me some images of things I did not have that allowed me to include it, but I did not get written permission from all of these people, so yeah.
What about this tool? Is this
The tool is all open source.
Great,
The
thanks.
tool is all open source. So you can take your own images and run them against this tool and basically get your results. And it allows you to compare, for example, you can run all the images on different models and you can compare how well different models did on the data. So you might see that the top one result for image classification was like 83%. On Inception and on VGG, it might be 79%. And on ResNet, it might be 82.5%. I mean, you can actually compare many different models. You can also compare different versions of the same model as you've trained it more and more, right? Or, and things like that. Okay, so I'm all done. If there's no more questions, I think I might have finished early.